There are nights in science when the data doesn't just update, it starts to feel wrong. For over a month, fireballs have been behaving like something turned the dial up on the entire system. A 4.5 sigma spike. Sonic booms in most confirmed events. Long-duration meteors breaking records we thought were stable. Then, Artemis II happened. 4 astronauts, 250,000 miles away, watching the moon go dark behind them. And then, it started flashing. 6 impact events in under an hour. Visible to the naked eye. No cameras, no algorithms. Just human vision confirming what Earth-based systems have been struggling to explain. And while all of this is unfolding, an asteroid slips inside the moon's orbit while they head home. So the question becomes uncomfortable fast. Is this just coincidence in a noisy sky? Or are we watching the solar system enter a new phase we don't yet understand? Stick around, because the next layer is where things start to get unsettling. Hit subscribe and stay close, because this story is not finished. Artemis II is moving straight into the most uncertain part of its trajectory. The lunar conformations, the fireball surge, the asteroid pass, none of it has resolved yet. This channel has followed this mission from the beginning. We're not stopping now. We will be here for whatever comes next. You will want to be here too. Now, let us get into it. 400,000 kilometers from the nearest atmosphere, in the absolute silence that only space can manufacture, 4 human beings watch the moon get hit. Not once, not twice, 6 times, in 57 minutes, with their own eyes. No camera processed that signal. No algorithm flagged it. No software model ran a probability check and sent an alert to a control room. It was just 4 pairs of human eyes, floating in a pressurized capsule behind the moon, watching something that our monitoring systems on Earth have spent decades trying to confirm from a distance, and they saw it happen over and over again in less than an hour. Let that settle for a moment before we go any further, because what the Artemis II crew witnessed during that observation window is not just an interesting data point. It is potentially a confirmation. And confirmations in science are the moment everything changes. To understand what they actually saw, you need to understand what a lunar impact flash is. When a meteoroid, a chunk of rock or metal moving through space at tens of kilometers per second, strikes the surface of the moon, there is no atmosphere to slow it down, no cushion of air to burn it up, no friction layer to spread the energy over time. It hits the surface bare. The kinetic energy of that impact converts almost instantaneously into heat and light. For a fraction of a second, sometimes a full second or two, a brief, bright flash appears on the lunar surface. It looks from a distance like someone briefly struck a match on the face of the moon and then immediately snuffed it out. From Earth, researchers at NASA's Meteoroid Environment Office have been monitoring these flashes using ground-based telescopes for years. Under normal conditions, the confirmed event rate sits at roughly 15 to 20 flashes per year across their monitoring network. That is about 1.5 flashes per month on average, caught by high-sensitivity charge-coupled device sensors pointed at the lunar surface during specific observing windows. Now, hold that number in your mind. 15 to 20 per year. And then consider this. The Artemis II crew saw 6 in 57 minutes. Now, I want to be precise here, because precision is what separates a real anomaly from a panic spiral. The human eye is less sensitive than a CCD sensor. The crew was not operating in an ideal controlled observation environment. And 57 minutes is a very short observational window from which to draw sweeping conclusions. The scientists will tell you all of this, and they are right. But here is the thing. They are still telling you something happened. The clustering itself, even after you apply every reasonable correction factor, does not dissolve into statistical noise. It sits there, unusual, demanding an explanation that nobody has yet provided. And what makes this moment particularly rare is the geometry. The crew was positioned to see the entire lunar near side simultaneously. On Earth, even the most sophisticated monitoring telescopes are covering a fraction of the lunar surface at any given moment. The Artemis observation window was, in effect, a full-face scan of the moon. When you account for increased field coverage, you expect to see more flashes than a ground-based system would catch. But the question is, how many more? Does the geometry alone explain 6 in 57 minutes? Or does the geometry only get you partway there, leaving a residual cluster that still cannot be explained away? That is the question that changes everything. And before we answer it, we need to talk about what Earth was already seeing before those astronauts looked out their window. The observation window the Artemis II crew had access to was not something you can replicate from the surface of a planet with an atmosphere. Think about what stands between you and the moon on any given night. You have weather. You have atmospheric turbulence that smears and distorts optical signals. You have light pollution from every city within your horizon. You have a monitoring system that covers, at best, a significant but still partial slice of the lunar disk. And you have the fundamental problem that Earth-based telescopes are working with a layer of air between them and the object they are trying to observe. And that air is never perfectly still. The Artemis II crew had none of those problems. In the vacuum of cislunar space, optical clarity is absolute. There is no air to scatter the light from a flash. There is no weather front rolling in to interrupt the observation. And critically, during the specific eclipse geometry that the crew was positioned within, sunlight was being blocked from the lunar surface, which dramatically improved the contrast conditions for detecting faint, transient events. Think of it this way: trying to see a struck match in a sunlit room versus a darkened one. The physics of contrast is on your side in the dark. This combination, wide field coverage, no atmospheric interference, favorable eclipse geometry, and human observers who were specifically positioned and alert, created something genuinely unusual in the history of lunar science. It created an off-world observation platform for a phenomenon that has only ever been measured from one side of the equation. Earth has always been looking up at the moon. This was the first time observers were essentially sitting next to the moon and watching it get hit. Now, I mentioned that the human eye is less sensitive than a CCD sensor, and I want to make sure that nuance is not lost. A charge-coupled device camera can detect events that are too faint for the naked eye to register. This means the crew was almost certainly not catching everything that was happening on the lunar surface. They were catching the bright events, the energetic impacts, the ones that produced enough light to cross the threshold of naked eye detection. In other words, they were not overcounting. If anything, they were undercounting relative to what a CCD would have recorded in the same window, and yet they still saw 6 events in under an hour. Which raises an obvious and uncomfortable question. If they only saw the bright ones, how many were there in total? That question does not have a clean answer yet, but it points towards something that is starting to make scientists who study the near-Earth environment genuinely uncomfortable. Because the Artemis observation does not exist in a vacuum, metaphorically speaking. It exists on top of a data set from Earth that was already, for weeks before those astronauts looked out their window, behaving in ways that nobody expected. Here's an idea that sounds simple, but is actually kind of elegant once you sit with it. The moon is, in a very real physical sense, a passive impact detector. It has been sitting in the same orbital slot for about 4.5 billion years, getting hit by whatever passes through the neighborhood. It has no atmosphere to burn up incoming objects. It has no global reporting network to amplify or suppress what hits it. It has no social media. It has no telescope coverage gaps. It has no bad weather days. Every meteoroid that reaches the moon leaves a mark, and every impact energetic enough to produce a flash produces one whether anyone is watching or not. This makes the moon extraordinarily useful as a kind of cosmic control group. When you study fireball activity on Earth, you are always wrestling with the noise in the system. Reporting rates change as smartphone camera density increases. Public awareness campaigns make more people look up. A single viral video of a fireball in a densely populated area generates thousands of reports, while a nearly identical event over open ocean gets zero. The Earth data is, to put it generously, messy. The moon does not have any of those problems. A flash on the moon is a flash on the moon. No amplification, no reporting bias, no network effects, just raw physics, happening in real time, on a surface we can observe. This is why the research community pays close attention when the phrase cross-validation starts appearing in the early discussions around the Artemis observation. Cross-validation in science means you have a signal from one system and you look for the same signal in a completely independent system to see if it holds up. Earth has been showing something unusual. The moon, if it confirms the signal, removes an entire category of explanations from the table. You cannot explain away an impact flash on the airless lunar surface by blaming it on reporting bias or camera saturation or a particularly enthusiastic regional news cycle. But here's where the scientific caution kicks in, and it kicks in hard because it has to. The moon observation was short. 57 minutes is not a statistically stabilizing sample. You cannot take a 57-minute window and confidently extrapolate a global rate change. What you can say is that something unusual appears to have happened during that specific window, under specific geometric conditions, and that it broadly aligns with what Earth data was already suggesting for the weeks preceding it. Whether that alignment is coincidence or confirmation is the argument that is now unfolding in real time. And if the moon saw it too, the implications are the kind that tend to keep planetary scientists up at night. Science rarely produces clean consensus, especially on short timescales with limited data. What it does produce, reliably and sometimes entertainingly, is camps. And around the Artemis II observation, 3 interpretive camps formed almost immediately. The first camp argues that the observation is primarily a geometry artifact. The crew's wide field coverage and favorable eclipse contrast conditions created an inflated detection opportunity. More surface, better contrast, more detections. Under this interpretation, 6 events in 57 minutes is not a signal of elevated meteoroid flux. It is simply a function of having a better seat in the theater. You see more when you can see more of the stage. The second camp accepts the geometry correction, but argues that even after you apply it, the clustering is too tight to dismiss as coincidence. Random events, even rare ones, do not tend to pile up in 57-minute windows. Clustering itself has statistical meaning. Under this interpretation, the geometry explains some of the elevated count, but not all of it, and the residual is worth taking seriously. The third camp, the most cautious and the most scientifically conservative, simply argues that 6 events is not enough to distinguish between the first 2 interpretations with any confidence. They are right in the strictest sense. A statistically stabilizing sample, this is not. But science does not always have the luxury of perfect datasets before it has to start asking better questions. What none of the camps could immediately resolve was the absence of synchronized Earth-based telescopic confirmation for the same specific observation window. In theory, if telescopes on Earth had been simultaneously monitoring the lunar surface during those 57 minutes with high-sensitivity cameras, you could compare detection rates and start to separate the geometry effect from a genuine flux signal. That data either does not exist in usable form or has not yet been cross-referenced and published. That gap is, frankly, one of the more frustrating aspects of this entire story. But here is the thing. Earth was not silent before the Artemis window opened. Earth had already been saying something loud enough to generate a 4.5 sigma deviation from baseline. and we need to go back about 30 days to understand exactly what that means. The American Meteor Society publishes regular reviews of fireball activity across the United States and parts of Canada and Mexico. Their network relies on a combination of dedicated all-sky cameras, paired radar systems, and public eyewitness reports that have been collected and calibrated over many years. It is not a perfect system, but it is a well-documented one, and its baselines are robust enough that when something falls outside the normal range, the analysts notice. In their first quarter 2026 review, the analysts noticed the deviation they recorded was 4.5 sigma from the established baseline. Now, if you are not a statistician, let me translate that for you in terms that actually mean something. A 1 sigma deviation means you are outside the range of roughly 68% of normal outcomes. A 2 sigma event is outside 95%. A 3 sigma event is outside 99.7%. At 4 sigma, you are in territory that, by pure chance, should only occur about 1 time in every 15,000 observations of that type. At 4.5 sigma, you are looking at something that, if it were pure random variation, would be extraordinarily unlikely to appear in a dataset of this size in a given quarter. The specific numbers were stark. The network recorded 38 high-report fireballs against a historical average of roughly 18. That is more than double. But it was not just the count that drew attention. Approximately 79% of those events produced confirmed sonic booms. Under normal conditions, sonic boom-producing fireballs represent a smaller proportion of total events, because they require both sufficient size and a specific entry trajectory to generate the kind of shockwave that reaches the ground. The proportion here was anomalously high. And then there were the long-duration sightings. Fireballs that stay visible for multiple seconds as they traverse the sky are rare because they require either a very shallow entry angle, a very large or dense object, or both. In the first quarter of 2026, the count of long-duration sightings ran approximately 2.5 times the historical record, not 2.5 times above average, 2.5 times the highest previous record. Now, does this mean something is definitively wrong in our solar neighborhood? Not necessarily. 4.5 sigma is rare, but rare events happen. Clusters happen. Anomalies that look terrifying in a single quarter sometimes dissolve into regression toward the mean by the following quarter. Scientists know this, and the good ones say it out loud. But the question is whether this particular cluster dissolves when you look at it from multiple angles, or whether it holds up and possibly gets weirder when you start cross-referencing with other datasets. Spoiler, it got weirder. Here's the thing about the fireball surge that makes the statistical argument harder to dismiss with a simple, rare things happen shrug. It was not just about how many events occurred. It was about what kind of events they were. And the shift in the distribution of event types is, in some ways, more scientifically meaningful than the raw count increase. Under normal conditions, fireball populations follow fairly predictable distributions. Most fireballs are small, fast, and relatively high energy relative to their size. They enter the atmosphere at typical sporadic meteoroid velocities. They burn up efficiently, and they produce brief, bright streaks that are over in 1 to 2 seconds. The system is consistent enough that analysts can characterize the background population with reasonable confidence year over year. What the first quarter 2026 data showed was a shift away from that normal profile. The events that were elevated were not uniformly distributed across the standard size and velocity ranges. The anomaly was weighted toward larger objects, toward slower atmospheric entries, and toward higher total energy releases per event. These are the characteristics of objects that have more mass, have traveled through more gravitational influence before entering the atmosphere, or both. Slower entry velocities in particular can indicate objects that originate from different regions of the solar system, or that have experienced some kind of prior fragmentation event that altered their trajectory. 2 HED meteorite falls. That is the class of meteorites associated with the asteroid Vesta and related differentiated parent bodies, occurred within 9 days of each other during this period. What made this particularly unusual was the spatial separation between the fall sites, which ran to roughly 98 degrees of arc across Earth's surface. 2 meteorites from the same geochemical parent group, falling 9 days apart on opposite sides of the planet. You can explain that with coincidence. You can always explain individual events with coincidence. But when you are stacking coincidences on top of a 4.5 sigma baseline deviation, the statistical burden of the coincidence explanation starts to get heavy. The important scientific caution here, and I want to be genuinely clear about this, is that all of this remains within the bounds of possible stochastic variation. Random systems produce clusters. The question that matters is not whether a cluster is theoretically possible under chance conditions, but whether the probability of this specific cluster under chance conditions is low enough to justify looking for a non-random explanation. At 4.5 sigma, with a distribution shift, with anomalous spatial separation in meteorite falls, the scientific community starts to have that conversation. And the conversation gets interesting when the standard explanations start to fail one by one. When an anomaly shows up in a monitoring dataset, scientists do not immediately reach for exotic explanations. They reach for the boring ones first, and they work through them systematically. Seasonal variation, new meteor streams, reporting bias, random fluctuation. These are the standard suspects, and in most cases, one of them closes the case without anyone having to rethink anything fundamental. The first quarter 2026 anomaly was unusually resistant to this process. Seasonal meteor variation is one of the first things analysts check, because Earth passes through known debris streams at predictable times of year, and those passages spike fireball counts. The problem is that the magnitude of the first quarter surge is far larger than any known seasonal variation can account for. The known streams that are active in that period are well characterized, and their contribution to the baseline is already baked into the models. Blaming the anomaly on seasonality requires the seasonal effect to be several times larger than it has ever previously been, which just creates a different version of the same problem. The second explanation that gets tested is the emergence of a new, previously unknown meteor stream. If Earth passed through a debris trail we had not previously cataloged, you would expect to see an increase in activity associated with a specific radiant. That is, a specific point in the sky from which the meteors appear to originate. If a new stream is responsible, the events should cluster around that radiant. The first quarter data does not show a clear radiant signature. The elevated events appear to be distributed across the sporadic background, that is, the diffuse, non-stream component of meteoroid flux that comes from all directions. New streams produce focused signals. This anomaly does not look focused. The third explanation is reporting bias. More cameras, more social media sharing, more people looking up. All of these can inflate fireball reports without any actual change in the incoming flux. This is a serious concern in any dataset that relies on public reporting, and the American Meteor Society data does. But here is where it falls apart. You cannot explain sonic booms with reporting bias. A sonic boom is a physical event. It either happened or it did not. The air either shook or it did not. The windows either rattled or they did not. The 79% sonic boom rate is not a reporting artifact. It is a physical measurement, and physical measurements do not inflate because more people downloaded a Fireball reporting app. The fourth explanation is random fluctuation, and this one is technically unkillable in a single dataset. You can always argue that 4.5 sigma events happen by chance sometimes. That is mathematically true. But when you combine the sigma deviation with the distribution shift and the sonic boom rate, and the long-duration anomaly. You are asking chance to explain not one unusual observation, but a correlated set of them. Each additional correlated anomaly multiplies the probability burden on the chance explanation. At some point, chance becomes a harder argument to make than causation. So, after systematically testing the boring explanations and finding all of them insufficient in one way or another, the scientific community was left in the uncomfortable position of having a real anomaly without a real explanation, which is exactly the moment when external validation becomes critical, which is exactly the moment when someone looks up and says, "What is the moon showing?" Science with uncertain data is also science with competing camps, and by the time the first quarter data was fully compiled and circulated among researchers working in this space, two broad interpretive positions had formed. They were not hostile to each other in the way that public controversies often become. Scientists generally manage their disagreements with more precision than that. But they were genuinely in tension, and the tension mattered. The conservative camp argued for statistical regression. Their position was essentially that 4.5 sigma events, while rare, are not impossible, and that the correct response to a single anomalous quarter is to wait and see whether the following quarter shows normalization. Unusual quarters happen. The history of meteor science has examples of short-term excursions that looked alarming at the time and turned out to be isolated blips. This camp was not dismissive of the data. They were appropriately cautious about it. They wanted more data before drawing conclusions. The clustering hypothesis camp took a different position. Their argument centered on the fact that the anomaly was not concentrated in the easily explained shower components of the fireball population. It was showing up most strongly in the sporadic meteoroid background, the component that represents the diffuse, non-stream material that fills the inner solar system. Sporadics are the hardest part of the meteoroid population to model precisely because they do not have clean orbital families with traceable parent bodies the way stream meteors do. But they are also the most stable component over long timescales. When the sporadics shift, something fundamental has changed in the background population, not just in one identified debris trail. The enhancement appeared particularly strong in the Anthelion source and in high declination sporadic streams. These are specific regions of the sporadic background that represent different dynamical populations within the inner solar system. If both of those regions are simultaneously enhanced, it suggests a relatively widespread change in the background flux, rather than a localized event. And widespread changes in the sporadic background are not easy things to explain with small local mechanisms. Neither camp had a mechanism. They had a description of an anomaly, a disagreement about how seriously to take it, and a shared recognition that the Earth data alone was insufficient to resolve the argument. What they needed was a completely independent measurement system that did not share any of the Earth network's observational biases. What they needed, in other words, was the moon. Every monitoring system has its weaknesses, and the Earth's fireball monitoring network has several that are significant enough to make skeptics comfortable discounting its anomalies. Reporting bias, as we already discussed, is real and measurable. Camera density across the monitoring network is not uniform, and areas of recent expansion will naturally report more events than those same areas reported 5 years ago, even if the actual incoming flux has not changed at all. Social media amplification creates feedback loops where a well-publicized fireball event makes more people aware that they should report fireballs, which increases subsequent reports, which creates the statistical appearance of elevated activity. These are not trivial concerns. They are the kinds of concerns that have derailed previous claims of fireball anomalies that turned out to be network artifacts rather than real flux changes. The history of meteor science includes several episodes where what looked like a genuine increase turned out to be a documentation increase. More cameras, more reports, more apparent events, same actual flux. Scientists learn from those episodes, and responsible analysts weight them heavily when evaluating new claims. The Moon has none of these problems, and that is not an overstatement. The Moon has no atmosphere to create reporting bias by selectively burning up some objects and letting others through. It has no camera network whose density can expand and create artificial inflation of recorded events. It has no social media community to amplify awareness of impacts. Every impact that produces a flash produces one according to the same physical laws, regardless of whether anyone is watching, regardless of whether the event gets posted online, regardless of whether it happens over a populous region or empty space. When the Moon confirms a signal, it confirms it with a cleanliness that Earth-based data cannot match. The Moon is, in the most literal possible sense, a raw physics measurement. And the Artemis II crew, positioned at a unique vantage point during a geometry window that has never been replicated in human history, turned the Moon into a real-time second detector running in parallel with the Earth network. Two detectors, same signal window, independent physical systems. In the language of experimental science, that is cross-validation. And cross-validation is where anomalies go to either die or become something that demands an explanation. The temporal alignment between what Earth was recording and what the Artemis II crew observed is the kind of thing that keeps analysts staring at timelines at 2 in the morning. The first quarter 2026 fireball surge on Earth was ongoing at the time the Artemis II crew conducted their observation. These were not two events separated by months or years. They were effectively simultaneous, running in the same window of time, recorded by two completely independent physical systems operating in different locations in the Earth-Moon system. On its own, that temporal coincidence proves nothing. Coincidence is always the null hypothesis that you have to defeat, and a single aligned window does not defeat it. What it does is change the probability calculus. If the Earth anomaly were the only signal, you might accept it as a network artifact or a rare statistical event and move on. If the lunar observation were the only signal, you might accept it as a geometry-enhanced detection window that produced misleading impressions of elevated flux. But when both systems show anomalous behavior in the same time window, the probability that both anomalies are independent, coincidences occurring simultaneously, begins to drop. The core inference here, and I want to be careful about how I frame this, is that the simultaneous behavior of both systems is consistent with a shared environmental condition. That is different from saying, we know there is a shared environmental condition. Consistency with a hypothesis is not confirmation of it, but it is the kind of result that moves a hypothesis from speculative to worth serious investigation, which in science is actually a meaningful transition. The alternative explanation that Earth had a coincidental statistical cluster at the same time the Moon happened to produce an anomalous observation count during a geometry-enhanced window requires you to accept two independent coincidences stacking on top of each other. That is not impossible. But in science, stacked coincidences are the thing you start becoming skeptical of when other explanations become available. And there is a deeper question here that the cross-validation raises without answering. If both signals are real, what generated them? What could cause a simultaneous elevation of meteoroid flux detectable both on Earth's surface and on the lunar surface across the entire face-on hemisphere of the Moon? That question points toward the solar system itself, toward mechanisms that operate at scales larger than any single object or event, and toward processes that we understand imperfectly at best. Let me introduce you to a concept that sounds mundane, but is actually one of the stranger aspects of living in the inner solar system. Every night, from every point on Earth, meteor observers are recording what are called sporadic meteors, meteoroids that do not belong to any known debris stream from any known comet or asteroid. They come from all directions. They have a range of velocities. They represent the background filling of the inner solar system with small debris, accumulated over billions of years from countless sources, broken up comets, collisions between asteroids, dust shed by inactive parent bodies, material scattered from the outer solar system by gravitational interactions. The sporadic background is not random in the way that word usually implies. It has structure. It has preferred source regions, called sporadic radiants, that represent populations of material in particular orbital families. The enthelian source is one of the major ones. It is associated with material in prograde, roughly ecliptic plane orbits that produces a relatively steady contribution to the background flux. High declination sources represent material in orbits inclined relative to the ecliptic, often associated with older, dynamically evolved populations. When both of those source regions show simultaneous enhancement, you are looking at an elevation of the ambient background rather than an event localized to one orbital family. And this is where the hypotheses that are circulating in the more speculative parts of the research community start to get genuinely interesting, even if none of them have confirmed mechanisms. One class of hypothesis involves gravitational perturbation events. In the inner solar system, the gravitational influence of Jupiter and, to a lesser extent, Saturn, is constantly nudging the orbits of small bodies. Major perturbation events, a close approach of a moderately large asteroid to a debris cluster, for example, can redistribute material in ways that temporarily elevate flux in certain orbital regions. If a perturbation event of sufficient scale occurred at the right location in the appropriate time frame, it could, in principle, scatter additional material into the Earth-crossing orbit population. A related class of hypothesis involves resonance-driven clustering. Orbital resonances with Jupiter can cause debris populations to clump in ways that produce temporary enhancements when Earth passes through or near those clumps. The inner solar system is full of resonance structures that we have only partially mapped. I want to be genuinely transparent here. None of these mechanisms has been confirmed as the driver of the first quarter 2026 anomaly. They are the kinds of mechanisms that make physical sense at a conceptual level, but have not been connected to a specific identified source event that would explain the observed enhancement. The honest scientific position is that we have a well-documented anomaly and a collection of plausible but unconfirmed hypotheses. The mechanism remains unknown. And that unknown mechanism is the thing that should be making everyone pay very close attention to the next several months of data. Because science is not a single voice, it is worth being honest about just how many different explanatory frameworks are currently being applied to the same dataset, and how little consensus exists at this stage. This is not a sign that the anomaly is not real. It is a sign that real anomalies in complex systems are genuinely hard to explain, and that anyone who tells you they have the definitive answer is probably moving faster than the evidence justifies. The geometry artifact alignment theory holds that the Artemis observation window, combined with the eclipse enhancement of contrast conditions, explains a significant portion of the elevated lunar detection count, and that the Earth surge is a combination of seasonal variation, reporting network expansion, and statistical fluctuation. Under this interpretation, the apparent cross-validation is a coincidence of two independently explainable anomalies. The short-term dust cloud redistribution theory suggests that a localized concentration of debris material has drifted into the Earth-Moon system's orbital path on a temporary basis, producing elevated flux that will normalize as the concentration disperses. This would explain the elevated count without requiring a system-level change in the background population. The resonance-driven asteroid fragmentation theory proposes that a fragmentation event in the asteroid belt, possibly triggered or amplified by a resonance mechanism, has recently contributed additional debris to the inner solar system, temporarily elevating the ambient flux. This would require identifying the parent body and confirming the fragmentation event, neither of which has occurred. The unknown stochastic clustering theory is the scientifically honest baseline position. Sometimes things cluster. We do not always know why, and the appropriate response is to collect more data and resist the urge to force premature explanations. What is not available yet is a single model that simultaneously and cleanly explains the Earth fireball surge, the distribution shift toward larger and slower events, the lunar observation count, and the temporal alignment of all three. Until that model exists, the question remains open. And open questions in science are, historically, the most interesting places to be. Because they are where discoveries live before anyone has had the courage or the data to name them. Let me now add something to this story that, in isolation, would be completely unremarkable. Near-Earth objects, the broad population of asteroids and comets whose orbits bring them into the vicinity of Earth, pass through the inner solar system constantly. The vast majority of them are small, non-threatening, and observed only by the automated survey systems that scan the sky looking for anything that might one day become a problem. Most of these objects come and go without generating any particular scientific interest beyond the routine catalog entry. During the same time window we have been discussing, a small asteroid in the 10 to 20 meter size range made a flyby at sublunar distance. That means it passed closer to Earth than the Moon is. This object posed no threat. Objects in that size range, even if they were on collision trajectories, would burn up almost entirely in the atmosphere before reaching the surface. The monitoring systems flagged it, tracked it, confirmed its trajectory, and moved on. What is worth noting is not the individual flyby, but the broader pattern of near-Earth object traffic during this period. Multiple additional objects passed within 5 lunar distances in a relatively compressed time frame. Each one was individually unremarkable. Each one was within the normal range of near-Earth object activity. Planetary defense teams did not elevate their alert status. No emergency protocols were triggered. The objects were small. They were tracked, and they were not dangerous. But they were there. And they were clustered in time in the same window as the fireball surge and the lunar observation. Now, I want to be careful here, because this is precisely the kind of pattern that the human brain is exquisitely designed to notice and to overinterpret. We are pattern recognition machines. We see faces in clouds and conspiracies in coincidences. The fact that multiple small asteroids were passing through the Earth-Moon neighborhood during a period of elevated meteoroid activity does not mean they caused it or are part of the same phenomenon. They could be unrelated. The orbital mechanics that govern near-Earth object trajectories operate on timescales and in phase spaces that do not necessarily correlate with meteoroid flux enhancements. But they were there. And in a story about anomalous convergence, the near-Earth object traffic is another data point in the same window. Draw from that what you will. While all of this was developing in the meteoroid and asteroid domain, the space weather environment was doing something worth noting. Electron flux readings in the near-Earth space environment showed an elevated period during part of the first quarter 2026 window. This was a sustained, multi-day elevation, not a brief spike associated with a single solar event. The NOAA Space Weather Prediction Center, which monitors these parameters continuously, was tracking the variation and providing the standard advisories to satellite operators and spacecraft mission planners. To be clear about what this means practically, elevated electron flux at the levels recorded during this period does not pose a health risk to astronauts in the Orion capsule. The shielding on Artemis II is designed for the radiation environment of cislunar space, and the crew was not in danger. What elevated electron flux does do is increase the sensitivity of spacecraft electronics to certain types of induced charging effects. Solar panels, sensors, and some onboard systems become marginally more susceptible to anomalous charging events when the electron environment is elevated. Mission operations teams factor this into their day-to-day planning. But let me zoom out from the practical operations level and look at what elevated electron flux actually represents. It represents an energized particle environment in the near-Earth space region. The mechanisms that elevate electron flux solar wind variations, magnetospheric dynamics, geomagnetic disturbances, are part of the broader space weather system that connects solar activity to conditions throughout the Earth-Moon system. When that system is in an energized state, it affects not just radiation readings, but the broader electromagnetic and particle environment that spacecraft and their crews operate within. The Artemis II mission was, therefore, taking place in an environment that was, and I want to be precise about this, not dramatically unusual, but measurably more active than baseline across multiple independent parameters simultaneously. Meteoroid flux elevated. Near-Earth object traffic clustered. Electron flux elevated. Each one explainable individually. All of them present at once. Here is a thing that scientists know, and that is worth stating explicitly for the sake of intellectual honesty. Human beings are among the most capable pattern recognition systems in the known universe, and that capability is also one of our most dangerous cognitive liabilities. We evolved to find patterns in ambiguous data because false positives, seeing a tiger that was not there, cost us less than false negatives. Missing a tiger that was there. We are biologically optimized to find meaning in noise. This means that when multiple unusual things happen simultaneously, our brains reach for a unified explanation even when the data does not justify one. I say this not to dismiss the convergence we have been discussing, but to be honest about the interpretive risk it carries. When you put the fireball surge, the lunar impacts, the asteroid traffic, and the elevated electron flux together in a single timeline, the narrative brain wants to see a single story. It wants a cause. It wants a mechanism. It wants the four anomalies to be one anomaly with four faces. That desire is powerful, and it is not always wrong. Sometimes a convergence of anomalies does reflect a real convergence of causes. Sometimes the unified story is the correct story, but sometimes it is not. Sometimes four unusual things happen in the same month because unusual things happen, and the human capacity to weave them into a narrative is doing more work than the data justifies. The orbital mechanics of near-Earth objects have essentially nothing to do with the electron flux environment, which has essentially nothing to do with the sporadic meteoroid background enhancement, which may or may not have anything to do with the specific impact flash clustering the Artemis crew observed. These could be four independent systems, each independently behaving at the edge of their normal ranges. The honest answer to the question, does this convergence mean something, is we do not know yet. The honest answer to, should we be paying attention to it, is absolutely, unambiguously yes. Because the consequence of ignoring a real signal is always greater than the consequence of investigating a false one. Different communities are reading this data very differently, and the fracture lines are not along the usual fault lines of believers versus skeptics. They are along disciplinary lines, and that is more interesting and more informative about how knowledge actually gets built. The engineering community, the people who build and operate spacecraft, is reading the convergence through the lens of statistical noise. Their job requires them to plan for worst-case environments and then fly through whatever the actual environment turns out to be. Elevated meteoroid flux is a factor in mission planning, but it is a factor that gets bounded by probability distributions and managed with hardware margins. Engineers are not dismissive of the anomaly. They are professionally trained to not be alarmed by it, because alarm is not a useful state for someone who has to make go or no-go decisions on specific technical systems. The planetary science and meteor research community is reading it through the lens of dataset integrity and causal mechanism. Their question is this a real signal or an artifact? And if it is real, what caused it? They are genuinely uncertain. They are gathering more data, and most of them are resisting the pressure to reach a public conclusion before the data justifies one. The public, the broad audience that encounters this story through news summaries and social media fragments, is reading it as a narrative. And narratives have protagonists and antagonists, and turning points and resolutions. The public narrative of this story already has a shape. Something strange is happening in our solar neighborhood. 4 astronauts confirmed it. An asteroid is passing close by, and nobody has a clean explanation. That narrative shape is compelling, and it is not entirely wrong, but it is also missing the uncertainty and the qualification and the "we don't know yet" that real science runs on. The fracture between these 3 communities is itself a data point. It tells us that this event is significant enough that different disciplines are investing energy in interpreting it. And that alone is worth paying attention to as the Artemis II crew begins the journey home. The Artemis II crew does not get to stay behind the moon, indefinitely contemplating what they saw. At some point, the mission profile demands a return trajectory, and that trajectory carries them back through the same region of lunar space that was producing anomalous readings while they were on their way out. The transit home is not a short hop. It is a multi-day passage through an environment that, by any objective measure, has been more active than baseline during the period surrounding this mission. The return trajectory takes the crew through what you might think of as the full environmental stack, the region where the electron flux variations were recorded, the orbital neighborhood where the near-Earth object traffic was clustered, and the general debris environment that produced the anomalous fireball rates over Earth's surface. None of these individually represent a mission-ending hazard. Orion was designed to operate in this environment. The probability of a mission-critical meteoroid impact on the spacecraft during transit is extremely low under any plausible flux scenario, even one significantly elevated above baseline. The capsule's structure provides substantial protection against the size of objects that dominate the sporadic meteoroid flux. But there is something both deeply mundane and quietly remarkable about the fact that the same crew who watched meteoroids slam into the moon from close range is now flying home through the environment that produced those impacts. They observed the phenomenon from one vantage point. Now they are inside it. They are not observers anymore. They are participants in the measurement. And on their way home, another asteroid is scheduled to pass inside the moon's orbit. Not threatening, not large, but there, as if the solar system is making a point. At approximately 25,000 miles per hour, the Orion capsule hits the upper atmosphere. This is not a gentle process. At that velocity, the kinetic energy involved is enormous, and the vehicle's heat shield, a system called Avcoat ablative material, handles that energy by deliberately burning away. The outer layer of the shield absorbs the heat, chars, and ablates, carrying thermal energy away from the underlying structure and the crew compartment. It is an engineered sacrifice. The shield destroys itself so the capsule survives. The Artemis I mission, which flew the uncrewed Orion around the moon and back, returned with char loss patterns on the heat shield that engineers analyzed carefully. The patterns were within design parameters, but they contained information about the specific thermal environment Orion encountered during re-entry, and that information feeds back into planning for subsequent missions. Every re-entry is also a measurement. Every heat shield that comes back charred and intact tells the engineering team something about the conditions at the boundary between space and atmosphere. Artemis II is returning from a mission that, by the data we have been discussing, took place in a near-space environment that was measurably more active than typical baseline conditions. Does that mean the re-entry will be more challenging? Almost certainly not in any way that the engineering margins do not absorb comfortably. The heat shield is designed with substantial performance margins precisely because environments are variable. The crew is as well prepared as any crew in the history of human spaceflight. But here is the paradox that I find genuinely interesting. The public anxiety around this re-entry is running higher than the engineering confidence warrants. The anomaly narrative, the fireball surge, the lunar impacts, the asteroid flyby, has created a perception of heightened risk that the mission's actual technical profile does not support. The engineering community is calm because the data tells them to be calm. The public is tense because the narrative tells it to be tense. Both are responding rationally to the information they have access to. They just have access to different information, weighted in different ways, and it produces a gap in how the same return feels from the outside versus the inside. That gap is a story about how we process risk, and it might be more revealing about our relationship with space than the anomaly itself. Let me lay out the situation with as much clarity as I can, because clarity is what this moment requires. Earth has a statistical anomaly. The first quarter 2026 Fireball data shows a 4.5 sigma deviation from baseline, with distribution shifts in event type, an anomalous sonic boom rate, and long-duration sighting counts at historically unprecedented levels. That anomaly is documented. It has passed through the standard skeptical filters, and it does not have a satisfying, conventional explanation. The Moon has an observational anomaly. The Artemis II crew recorded 6 naked-eye impact flash events in 57 minutes during a geometry-enhanced observation window with no atmospheric interference and no reporting bias. That count, even after adjusting for the geometric advantages of the crew's vantage point, does not fully dissolve into a mundane explanation. The clustering remains. The mechanism that would explain both anomalies simultaneously does not currently exist in confirmed form. There are hypotheses: sporadic source amplification, gravitational perturbation, resonance-driven redistribution, but none of them have been connected to a specific identified source event that definitively closes the loop. We have 2 well-documented deviations from expected behavior in 2 independent physical systems, a temporal alignment between them, and a gap where the causal explanation should be. This is the asymmetry problem. The data is ahead of the theory. We know something happened. We can describe it with some precision. We cannot yet explain it with confidence. That is an uncomfortable place to be, and it is the most scientifically honest place to be. And those 2 things are not a coincidence. Comfort in science usually means you have settled for an explanation before the evidence fully justifies it. Discomfort usually means you are taking the data seriously enough to sit with what it is actually telling you, rather than what you wish it were saying. The asymmetry between data and explanation is not a failure of science. It is science working exactly as it should, in real time, with imperfect information, in a universe that is under no obligation to make itself easy to understand. So let us bring all of this together, because you have been patient, and you deserve the most honest summary I can give you. Over a period of roughly 6 to 8 weeks, the following things happened. Earth's Fireball monitoring network recorded a 4.5 sigma deviation from historical baseline, with elevated counts, anomalous distribution shifts, an unusually high proportion of sonic boom-producing events, and long-duration sighting records at historically unprecedented levels. The sporadic meteoroid background showed enhancement in multiple source regions simultaneously. 2 HED meteorite falls occurred 9 days apart with anomalous spatial separation. Multiple small near-Earth objects made flybys in a compressed time frame. The near-Earth electron flux was elevated for a multi-day period. And then, into this already unusual picture, 4 astronauts orbiting the Moon watched meteoroids hit the lunar surface 6 times in 57 minutes. These events admit 2 broad interpretive frameworks. Under the conservative framework, each anomaly has an individual explanation within the range of normal stochastic variation and observational artifact. The temporal alignment is coincidence, and the appropriate response is to collect more data and wait for regression toward the mean. This interpretation is scientifically defensible, epistemically responsible, and possibly correct. Under the more expansive framework, the convergence of anomalies across independent physical systems and independent detection methods in the same time window reflects a genuine, temporary elevation in the ambient meteoroid flux environment of the inner solar system, possibly driven by a mechanism in the sporadic background that has not yet been identified. The lunar observation cross-validates the Earth signal in a way that removes the most obvious confounding explanations. And the return of the Artemis II crew through the same environment, while another asteroid makes a sublunar pass, closes the window on one of the strangest observational periods in the recent history of near-Earth space science. This interpretation is also scientifically defensible. It is not fringe. It is not conspiracy. It is the straightforward reading of a convergence of anomalies that deserves serious investigation and has not yet been resolved. The truth is probably somewhere in between, and we will not know where exactly until the subsequent quarters of data either show normalization or show persistence. If the fireball rates return to baseline in the second quarter of 2026, the conservative interpretation gains ground. If they stay elevated, if the sporadic enhancement persists, if additional observation windows from future cislunar missions show continued anomalous impact rates, then the expansive interpretation becomes harder to dismiss. The Artemis II crew is coming home. They carried with them the most unusual observational dataset a human crew has ever collected from the vicinity of the moon. They saw something that our ground-based systems have been measuring imperfectly for decades, and they saw it with their own eyes, from a position no human had ever occupied before, during a geometric window that may not recur for years. What they saw may have been a cluster of coincidences in a 57-minute window during an anomalous but ultimately self-correcting period in the near-Earth environment. That is possible. That is maybe even probable. Or it may have been confirmation that something in our solar neighborhood has shifted, not catastrophically, not dangerously, not in any way that alters the day-to-day lives of 7 billion people living at the bottom of this atmosphere, but shifted, changed, moved slightly off the baseline that we have spent decades carefully measuring and assuming to be stable. We live in a solar system that is 4.5 billion years old and still actively dynamic. Debris is redistributed constantly by gravitational interactions we can only partially model. The inner solar system is not a static environment. It is a living system, operating on timescales that dwarf human history, and occasionally, rarely, quietly, without announcement, it enters a different phase. The astronauts watched the moon get hit 6 times in an hour. The Earth had already been telling us something for weeks. The question is not whether these are interesting data points. The question is whether we are asking the right questions before the signal disappears back into the noise. Because the hardest kind of mystery is not the one that announces itself. It is the one that leaves quietly before you figured out what it was trying to say.